And it's an honor for us to have another webinar from ReThink on circularity, circular reconstruction, and green recovery of Ukraine after the war. This time we do it within the S3 project, which is Safe, Sustainable, and Swift Reconstruction of Ukraine, focused on concrete upcycling from war debris. It's quite a unique project, and we decided to hold this webinar to explain importance of circular concrete in general, but also to highlight what we are particularly doing in the S3 within the activities of this project. And to me, it's a great honor to have distinguished speakers today. Leon Black, professor of University of Leeds, who has dedicated more than 20 years to the research in this area, and Martin Paterson, Chief Operating Officer of Everox, the technology provider within the S3 project, and the leading company in the world in concrete upcycling. I see Leon's camera disappeared, but I hope he's still here. And yeah, you're still here. So without further ado, I would just give the floor to Leon. So the sequence will be the following. We will hear from Leon. We will have a Q&A. You are very free, and I encourage you to ask your questions in the Q&A underneath the screen. And we'll have some discussion after his lecture. Then Martin will connect in about half an hour. We will hear from him, and then we will have a joint Q&A in the end. So we thank you very much for your interest, and let's begin. Leon, the screen and floor and mic and everything is yours.
Thank you very much, Roman. So good morning, everybody. Just let me share my screen. And we'll be there in a second. There. I hope you can all see my screen. So as Roman has said, I'm Leon Black. I'm Professor of Infrastructure Materials at the University of Leeds. I've been working on cement and concrete for over 20 years now. And for the last, it's been about 5 or 6 years with a particular focus on circularity. So how can we maximize the reuse of end-of-life concrete? How can we make concrete more circular? So as Roman has said, the talk is based partly on various projects that I've had running in Leeds in recent years, but also it's framed within this concept of the S3 projects, Safe, Sustainable and Swift Reconstruction of Ukraine. This is a collaboration between the University of Leeds, University of Sheffield, University of Oxford, Imperial College London in the UK, then in Ukraine, National University of Water and Environmental Engineering, and Lviv Polytechnic National University. From industry, we have Everox in the Netherlands, ReThink and EcoPlus Logic in Ukraine. So the aim of S3 is we want to transform war and disaster rubble into a sustainable future. That's the short summary of the aim. What we're really looking to do is how can we support the reconstruction of Ukraine following the destruction being wrought on it by Russia's illegal occupation and invasion. We want to use our understanding of technology to transform post-conflict rubble into a more sustainable future. We want to use it to total recycling of the end-of-life concrete. And whilst the focus is on Ukraine, we're hoping that the technology is equally applicable to other post-reconstruction operations, be those post-conflict, for example, in Gaza, also though post-natural disasters. Okay. So The structure of my talk I've split into 4 sections, starting off by saying why concrete has an environmental problem. Then I want to talk about recycled concrete aggregates and what they are. Then how these recycled aggregates behave when added to fresh concrete. And finally, I want to say how can we valorize or reuse recycled concrete powder, which is often considered somewhat of a problematic material for recycling, but actually holds great potential. Now, concrete has a problem. We use anything up to 30 billion tons of concrete each year, and that requires 4 billion tons of Portland cement. As a result of that, Portland cement production itself is responsible for anything up to about 8% of global CO2 emissions, and the concrete production is around 10% of global CO2 emissions. In addition to these carbon emissions, there's also huge material consumption. Sand, for example, this was a report in India that sand is being extracted faster than it can be replenished. And actually, I was amazed to find out organized crime is involved in sand mining. I guess wherever there's money to be made, there's criminality involved as well. But it's causing this environmental degradation. And we're trying to then say, well, what can we do about it? So if we're going to more statistics around concrete. I've already mentioned the quantities of materials being used. But if we specifically look at end of life concrete, we produce 700 million tons of construction and demolition waste, CDW. We produce of this 700. Of this 700 million tons of construction and demolition waste, about half of that is concrete, so 350 million tons per year. We know that this can be recycled, but that doesn't necessarily mean that it is recycled. In the UK, the official figures are that just under 94% of construction and demolition waste is recycled. But often this is in very low value operations. So the figures on the right hand side show a typical example. This isn't from the UK, but there is construction and demolition waste, and really it's being reused to fill a hole. Now, we can do far, far more than that, and we should do far, far more than that. And this introduces the concept of a circular economy. Okay, our current system is this linear economy, as shown. Well, many of you may have seen this figure before from Circular Flanders, but it shows a linear economy. Take, make, break. We extract materials from the ground, we make something with them. When they're used, when they're finished with them, they're broken, we throw them in a bin. Okay, and we're now moving towards a more of a recycling economy, where we may use something 2 or 3 or many times, and then ultimately it is still ends up being thrown in a bin. We dispose of it. The circular economy, however, what we're trying to do with the circular economy is introduce this concept of maintaining value within a system. Can we continually reuse a material with this minimal loss of value, just to use resources more efficiently? Now, for monolithic concrete, this is a problem. Most concrete is cast, not as prefabricated units, but sorry, fire alarm is going off here. It's in the building next door. I'm okay. Right. Apologies. That wasn't planned. So, monolithic concrete can be a problem. We cast concrete into formwork, and it has the reinforcement. We have the reinforcement integral within this concrete. It makes it very difficult to deconstruct and reuse that material. And conventional demolition, either planned or post-conflict, leads to considerable loss in value. So from this circular economy perspective, where we're wanting to maintain value, it becomes a problem. A concrete beam that's turned into rubble no longer performs its structural purpose. It loses economic value as a beam is converted into rubble, because rubble is far, far cheaper than monolithic concrete. And it also loses carbon. We take concrete with a carbon footprint of typically 250 kilos per cubic meter, and we're using it to replace, typically at the moment, aggregate that has a carbon footprint of 15 kilos per cubic meter. This is an incredible loss. Okay. So what else can we do? Well, if we're going to do things with end-of-life concrete, we need to know what it is. And we can consider end-of-life concrete comprising of three components. We have your recycled coarse aggregates. These are gravel, stones, between 4 millimeters and typically up to 20 to 40 millimeters in diameter. Then we have recycled fine aggregates. It has particle size from 150 microns to 4 millimeters. And then we've got recycled concrete powder, so a fine material less than 150 microns in diameter. The figure on the top right shows recycled coarse aggregate. This was some material that was prepared in our lab. You can see so that piece, a larger piece on the left-hand side. Can I just ask, I don't know, can people see my cursor when it's moving on the screen?
I think so. Yeah, we can see
Yes.
that.
Okay. Right. Because I'm pointing to things on the screen, and I don't know. I normally use Teams, so I don't know whether Zoom allowed me to do this. So yes, this piece of aggregate here, about 30 millimeter in diameter, 30 millimeters long, about 20 millimeter in diameter. But you can make out this is the original aggregate, and it has mortar stuck to it. And this can be better seen through a schematic. The schematic here we show original aggregate, and there's old mortar stuck to the outside of it. Now, an important feature of concrete is what's known as the interfacial transition zone, this ITZ. And this interfacial transition zone is the point where the cement paste touches the aggregate. That's a point of weakness. And in normal aggregate, in normal concrete, you just have this interface between the aggregates and the mortar. But in recycled aggregates, you have your original interfacial transition zone. You can have an interfacial transition zone between original aggregate and new mortar, or between adhered mortar and new mortar. And these ITZs, these interfacial transition zones, are points of weakness. And we need to know more about these if we're going to improve our understanding of end-of-life concrete. Now, I want to show this quote. This was one of my starting points for looking at recycled materials. Thomas Rau is an architect, founded a company, Madasta, that looking to develop material banks, or considering the built environment as a material bank. And his quote from Thomas was, "Waste is material without identity. If we don't know what we can do with a material, we end up throwing it away." And so really what we want to do is say, how can we, let's start with, what is recycled concrete aggregates identity? Okay, what do we know about it? Well, we know that it's relatively inert, because otherwise it wouldn't survive within a concrete matrix. We know that it's dimensionally stable. We can't squeeze it, and it's not going to deform if we squeeze it. And we also know that it contains this adhered cement paste. Okay, so we know its size. We know that it's not going to rot, and we know that this cement paste exists. That really is all we know. We know the quantities as well. So this figure on the right, I'll come back to this. This shows mix on the left-hand side. These were the components going into some laboratory concrete that we were making. It was used as part of a PhD project, and then we crushed it to do some studies that we were looking at. So we found that about 60%, 70% was recycled aggregate, so coarse aggregate, more than 4 millimeters in diameter. And then worked out about 15% each of recycled concrete paste and recycled fine aggregate. Okay. So what do we know? What is recycled concrete's identity? It's inert. We know how much of it. We know how its size, and we know that it's dimensionally stable. At which point, if that's the only information we have about the recycled aggregates, we end up saying, okay, we will now just use it as backfill. We will use it to fill a hole on the site, or we will use it as sub-base on which we can build a new road. And that's this significant downcycling that we have with end-of-life concrete at the moment. So can we give recycled concrete more of an identity? What can we find out? What can we learn about recycled aggregates that by understanding these properties, it allows us to make better use of the materials? So this photo here, this is taken from the laboratory concrete. This was crushed aggregate. It's very angular. It contains lots of adhered mortar. And then we processed it. We basically tumbled it in a mixer to remove this adhered mortar. And this is what we were left with at the end. And then looking at each particular size fraction, we measured the amount of cement paste that was stuck on each aggregate, and we measured the water absorption capacity. That's you take dried aggregate, little more than dried aggregate, put it in a bucket of water, and measure how much water is taken up and soaks into this slightly porous aggregate. And we found that as the amount of paste increased, the water absorption capacity increased. That's a problem for concrete, because this water absorption, if that water is taken into the aggregate, it stops the concrete from flowing. Contractors don't want to work with very stiff concrete. They want to be able to, I was once told, they want concrete to flow like water. Anything less than that is a problem. Okay, so this water absorption capacity is a problem because it reduces the flow. We know that the increased paste content is also a problem because more paste means more interfacial transition zones, so these points of weakness, which weakens the concrete. But whilst we can do laboratory work to give this recycled aggregates an identity, to learn more about it, there are just realistically too many variables that can affect performance. The aggregate size and type, that's related to the water absorption capacity. As you get smaller aggregates, you get more adhered mortar, you get greater water absorption. You get a change in the relative proportion of surface that is interfacial transition zone. And it just becomes incredibly complex. And whilst we can understand it conceptually, we don't have the resources really to look at every single variable. So what we started to do, and we're doing this part of one project and we're doing it in S3 as well, we're looking at data mining. There is lots of work going on around the world on recycled aggregates. We found 750 published mixed designs. These had all been through peer review, so they all, in theory, validated. And we found 78 input variables. So everybody reports how much sand, how much water, how much aggregate, how much cement. Some people report the size of the aggregate, some people don't. Some people report the water absorption capacity of the natural aggregate that was used, some people don't. So we identified 78 different variables. Of these 78, 36 of them had less than 10% missing data. Okay? And that's important because the smaller the percentage of missing data, the better that we can impute. So we can use mathematical formula to fill in the missing data. We also identified 13 output, before talking. So these 36 input variables and the imputation. This is shown, for example, the right-hand side. This is a histogram of water absorption against the number of mix designs of a given water absorption. Natural aggregates have a low water absorption. Recycled aggregates, a much broader distribution of water absorption. But we can model this with a mathematical distribution, and we can say then that if there is a study that doesn't report the water absorption, we can look at the other properties of this mix and make an informed estimate of what we think the water absorption capacity would be. That's this imputation. Okay, and that was done within input variables. There were also 13 output variables. Okay, these are things everybody reports: 28-day compressive strength. Okay, some people report 7-day strength, some people report 56-day strength, some people report slump or density or any one of a number of different output variables. And there were 7 that had less than 10% missing data, so that we could impute. When we plotted for the 750 mix designs, we plotted the percentage of recycled aggregates in the mix versus the unconfined compressive strength at 28 days. And we can see that because of the interfacial transition zone, there is a general drop in strength, ever so slight, but there is a huge scatter in this data. Okay, it becomes very difficult to say with confidence that this is our trend line when there is such significant scatter in the data. So we had to think, what else could we do? Well, if we know that there is this loss in strength, we plotted the percentage replacement against the change in strength. And we can see here that the result is a little bit, there is a general reduction in strength versus the replacement, but there is still a lot of scatter in the data. And this is where having these other input data, so such as, for example, the water absorption capacity, becomes important. We started to plot now the water absorption capacity, or the strength in reduction, as a function of replacement ratio for mixes with different water absorption capacities. If there was a water absorption capacity over 5.8%, which is quite high or very high, there was a more significant drop than if we could get the water absorption capacity between 4 and 5.8, or better still, be less than 4. If we actually get it below 3%, we're in a position where we can start to say that this material is behaving very similar to that of, or to natural aggregates. So we need to understand how can we remove this adhered mortar. And this is what some of the work we've been doing in Leeds, and it's also some of what Everox are doing as part of their project in S3, which you'll hopefully hear about later. So we then said, we've got this recycled aggregate. Instead of the modelling, we're now looking back in the lab and saying, how does this material behave when you put it in concrete? So we made concrete with 100% recycled aggregate. We replaced all of the sand, we replaced all of the natural aggregates, and just used recycled and processed coarse and fine aggregate. Because of the adhered mortar, there was a loss in slump. Okay, so the concrete didn't flow quite as well. If we go from our control mix with a slump of 140 millimeters, it dropped to 8.5 millimeters. But we could add a bit of additional water to that and it corrected for the slump. Or we could add a super plasticizer and that brought the slump back to where it should be. When we compared then the 7-day and the 28-day strength, we actually saw that by processing the aggregates, there was no significant loss in strength. Indeed, there was actually in some instances a slight increase in strength. But this is because we've taken the material that we'd used in Leeds was a rounded aggregate, and then once it had been crushed, it became slightly more angular. That led to a slight increase in strength. So we were able to see that there really wasn't loss in performance. We could correct any loss in slump, and so we could make concrete that's comprising entirely of recycled aggregates. But can we go further than that? So we know that processing the aggregate improves performance, but going back to our work earlier where we looked at this what's known as a Sankey diagram, so that's looking at material flow, we know that about 12 to 15% of our recycled aggregate ended up as being powder. So this is material less than 150 micron in diameter. We also knew that when we looked at the composition of this, about 80%, so that's the blue material, was cement paste, and about 20% was recycled, was crushed quartz fines from the sand. So we said, well, what can we do with this? And this is important because if you look at the carbon footprint of concrete, this cement paste actually accounts for about 90% of the carbon footprint. And so we're trying to say, well, how can we maintain some value within the system? If you think back earlier where I was saying that there was a loss in carbon value from monolithic concrete to recycled concrete, we're trying to say, well, can we reclaim that cement such that we're no longer having to have new concrete with quite the same high carbon footprint? So we looked at this material that was 80% cement paste. Ours was 80% cement paste. I've seen other samples anything between 60 and 80%. And we activated it by either heat and or carbon dioxide. Okay, heating drives off the water and can ultimately lead to some phase changes. Adding carbon dioxide strips calcium out of your cement paste, converts your recycled cement paste to a mixture of calcium carbonate and an aluminosilicate that can act as what's known as a supplementary cementitious material. So it can be blended with cement, producing additional cementitious binder. Okay, and the standard test to assess the performance of a supplementary cementitious material is what's known as an activity index. You take 80% cement, 20% of your material, and if the compressive strength is greater than 75% of that of a reference mix, it's considered to be a suitable cement replacement. What the table shows here is a range of the original material plus 6 different treatments. The as received material has activity of 60%. It's below this threshold. But all of the other treatments, either heating or carbonating, improved performance sufficiently that they could be considered as suitable cement replacements. Actually, combined carbonation followed by heating actually gave performance comparable to that of cement. Okay. But we didn't want to stop there. And what we're doing is within S3 at the moment is to say, well, can this recycled cement paste also be used not just to replace cement, but can we use it to produce cement? So can we take recycled concrete powder and use it as a raw material for low carbon cement production? One of the reasons why cement has such a high carbon footprint is that the raw materials, or one of the raw materials used for its production, is limestone. And when you take the limestone and blend it with clay, heat it up to 1400 degrees, you produce cement. But that heating process, as well as the energy, gives off carbon dioxide from the breakdown of the calcium carbonates of the limestone that is used to make cement. If you use recycled concrete powder, you no longer have that CO2 that's given off during production. So you can significantly reduce the carbon footprint of your cement production. We're also looking at low energy approaches to reducing, to producing cement. So using a microwave. Can't show any results on this because, what day are we today? We're Thursday. No, this microwave furnace is actually installed tomorrow. So, but it's all the samples are ready to go. In conclusion, it was just a light overview of what has been done. We need to do something more with end-of-life concrete than bury it as construction and demolition waste. We know that recycled aggregates can be used, albeit sometimes with an ever so slight loss in performance. But additional processing can improve this performance such that you can get performance comparable with natural aggregates. The key thing here is removing this adhered mortar. However, that does have some carbon implications. It uses energy to process. It has financial implications. It costs money to process. But by separating and removing this adhered mortar, you can valorize the material. The cement paste that's produced from that can be used to either produce a supplementary cementitious material, so reducing the carbon footprint of your concrete, or to produce a new cement itself. That's pretty much it from me. I want to say thank you to various colleagues over the years who've supported me here. Boral, Ehsan, Ali, Bruno, Hassan and Theo, all in Leeds. Maurizio at the University of Sheffield, who are working with an S3. James, who project manager and keeps us all on track. And Alexei Hunyak and Taras Markiv from NPNU, who I did fortunate enough to actually meet in person a few weeks ago when they were able to travel over to Leeds. Finally, want to say just thank you to all of you for your attention, and happy to take, if you want more information about the project, then please scan this QR code. But happy to take any questions. Thank you.
Thank you, Leon. Thank you. This is incredible how you resisted this terrible noise that you're having
I know. I hope it
in the
didn't.
room. No,
I hope
no,
it wasn't too much of a distraction.
for me and for us, we could hear you well, and yeah, I just cannot imagine how is it to speak when you hear all that next to you.
It was
So
a bit of a distraction. Yes.
thank you so much for such a professional and insightful speech. Very interesting to me. I will keep my questions till the end. There are some already, but I would then, since Martin is already here, I would just go on, and then let's make Q&A in the end. That will be more interesting to combine also answers from both of you. Martin, hello. Can you hear me?
Hi, good morning. Loud and clear.
Yes, thank you so much for joining. So I will pass the floor to Martin Paterson from Everox, Chief Operating Officer. Everox is a company based in the Netherlands, Rotterdam, and is the technology provider within S3, and also one of the leading companies in circular concrete innovation in the world. So the floor is yours. We can see your slides. So yeah.
Okie doke. Thanks for introducing Roman. I'm very happy to be here. My name is Martin. I'm co-founder and chief commercial officer of Everox. And yeah, also thanks to Leon. I only could listen in the last minutes, but I think you did half of my job already by explaining all the good benefits of the recycled cement paste and how we can use it further. For us in Everox, this is of course the key. The key of our process is basically to separate the old cement paste from the aggregates as much as possible, and then activate the cement paste afterwards again, so we can use it as an SCM. I will start explaining a little bit about the company, about Everox, where we are, what we are doing, but then also at the end have a quick view on our wonderful project which we're having in our consortium, and also give a quick outlook of the Ukrainian market. So let me get started. Our vision is to reduce global CO2 emissions by 2%, and that might sound very ambitious. It is very ambitious. And we need to build approximately 12,000 plants to do that, but we still believe this is possible, and this is where we should be. A little bit about the cement challenge. I think Leon also talked about it already. We have 8% of the global CO2 coming from the cement production, approximately. If you look at this graph on the right side, I will try to get a pointer. So currently, the world is producing approximately 4 billion tons of cement per year with a clinker factor of 70%. That means the CO2 emitting part, the clinker, has already been reduced. We're already using additives like gypsum, like slag, like fly ash. And moving forward, this is expected to grow. So since cement is a hard to abate industry, it's one of the most sustainable building materials still. The cement consumption will grow. We will build one New York City every day until 2050. So we need cement. And the question is, how do we make it more sustainable? And there are different scenarios about it. This one is taken from the German DVZ, which says we can produce a compatible cement with only 35% clinker factor. So if you look at that numbers, there's a huge gap in the future coming up. I think Leon also alluded 60% of the calcining, 60% of the emission comes from calcining the limestone. We have an increase in cement consumption. The current additives we're using, which is mainly slag and fly ash at the moment, they are getting scarce. So fly ash is a byproduct from the coal-fired power plants, and we're using them less and less. Slag comes from producing steel, and there also the production material, the production process changes, going away from furnace production more to hydrogen, which also then makes slag less and less available. So the industry is really looking for alternatives. One thing is, of course, the scarcity of the current additives, but then also if you look at this chasm which you have from now until 2050, we're looking at roughly 2.5 billion tons of SCMs, which we need per year. And the question is which ones can be used, and it has to be a combination. But definitely, concrete waste is a very promising and good alternative. Not only because of the high reactivity and the high potential, which Leon already explained, but also due to the availability. So if you look at the global market, there's roughly 3.5 billion tons of concrete waste which is being produced every year. And that doesn't consider the landfills we have made over the last decade. So this is newly produced feedstock. And if you talk about 3.5 billion tons of feedstock material, you're talking about roughly 1 billion ton, 1 billion ton of cementitious product, which is at the moment being landfilled, thrown away, or used as road-based aggregate, so downcycled. And this is the material we have to recover. And that is, if you remember, the 4 billion tons of annual production, that's 25% of the global cement production. And that is the 2% we are targeting to reduce the carbon footprint with only one technology, with only one SCM. So please keep that in mind. Another good thing about concrete waste is that it's available close to the point of use. So you don't need to drive to any mine tailings outside there or in the mountains to find some seldom stones. This feedstock is available in the big cities where you're building it again. So you can, on top of having the availability, you have almost no logistics if you do it right. And that makes it a really circular, high available SCM for the future. And that really determines our mission in Everox. We want to phase out virgin materials in concrete completely and make use of local available circular product which can be used in order to build the future of tomorrow. Just a quick reminder of how it works. So in principle, today we have deep quarries where we get the raw materials, we put it into some cement plants to produce clinker or cement. Out of that, we produce construction materials, we build the buildings, and then after the end of the lifetime, 20, 30, 40 years, the building is being demolished again. And nowadays, best practice, being landfilled or in the best case, being downcycled to make use of the aggregates in it. What we are doing in Everox is we want to close that circle by crushing the material, separating it, using different technologies to have a more advanced separation, and then finally activating the old cement paste so that we can put all of our products back into that circle and thereby reduce the requirement for primary materials. This is what we call the concrete circle, and this is what we're working on. So a little bit more in detail, how does our patented process work? We receive end-of-life concrete on site. We do crushing in 2 stages. The essence of the crushing is to keep the integrity of the primary materials. We don't want to destroy the stones. We want to more rub off the bound between the cement paste and the stone. Out of that crushing process, we get a 0 to 60 millimeter material, which goes into our ballistic separator. In the ballistic separator, we get 3 fractions out of that machine. Basically, it's a fast-turning rotor which hits the material, and then by depending on the particle size and on the weight of the material, we go to different areas of the machine. So we get 3 fractions out of that. Number 1, and that's why it's here in orange, is the recycled coarse aggregates. This material is measured with high-speed cameras at the outlet. If the quality is good enough, then we take it out of the process and we can use it as a replacement of natural gravel. If the quality is not good enough, we still have too much cement paste on it, we recirculate it, we put it back into the crushing and run it one more time. The 1 to 4 millimeter fraction is actually the one which is the most difficult to clean. That's the small sand particles with still a lot of cement paste around it. Very difficult to use in construction because it has a super high water absorption if you don't clean it properly. So we put it into what we call the thermomechanical separator, our TMS. So you have the stone, you have the cement paste around it. We shock heat that bound so that at a temperature of 350 degrees, the stone expands while the cement paste shrinks, and then you crack off the cement paste from it. So it's a very efficient way of cleaning the sand, and accordingly we get a very dry and clean sand out of it, high quality with a water absorption actually below 6%. We call it recycled fine aggregates. That's the orange one here. And the cracked off cement paste we call it the ultra fines. So I must say, until here, there's a lot of technologies, meanwhile, worldwide. Other companies who are doing that, some are doing it in a dry process, some in a wet process. They somehow crush concrete, they somehow separate it. But as I said at the beginning, for us, the purpose is, until now, just to remind you, keep the integrity of the aggregates, take off as much cement paste as possible from them, and then use the fines from the ballistic separator and the ultra fines from the thermomechanical separator to go into the last process step, which is the activation. So we don't only want to use that material as a filler in concrete or in cement. We want to use it as a reactive binder, and thereby we need to activate it. And again, Leon also introduced some different options to activate it. What we are doing is we start with a selective grinding process, so mechanical treatment, where we only grind the amorphous content. Leon also said there's still a lot of silica in that, depending on where you are in the world, depending on the nature of the concrete waste, more or less. Here in the Netherlands, we see up to 40% silica in that fines. So we only want to grind the non-aggregate part, and that's what we do it by selective grinding. And then after the grinding, we do a silica depletion. So we have an air separator where we can then take out the quartz content, and that's what we call the fine inert filler. So this is also a final product which you can use. This is 90% pure quartz. You can use it as a filler in concrete or even for other industries. So we're talking, for example, to the glass industry, which are very interested in that material as a grinding component. But again, our main focus is on cleaning up the cement paste, getting the silica out of that, and then we're basically using the CO2 coming from the flue gas of the thermomechanical separation, so our own internal CO2 source, to carbonate the material. And that's what comes out of that is the activated cement paste. And I will explain afterwards a little bit about the quality of that material. So in summary, in a nutshell, we put waste concrete into our process without any waste, without any byproducts. We get, depending on the nature of the concrete, but this is a good rule of thumb, 60% RCA, 15% recycled fine aggregates, then a small amount of fine inert filler, and roughly 20% of the activated cement paste. And looking at the quality of that materials, what we see now on a constant basis is that the aggregates we get out of it are very clean and can be used to a high degree in concrete as replacement of primary products. So the coarse aggregates has a water absorption level below 4%, the fine aggregates below 7 or even below 6%, as I said. And the activated cement paste, I will show more details about that later, but from the reactivity perspective, we are in the range of Class F fly ash at the moment. So here's just a quick overview of different SCMs, and of course, a little bit depending on how we produce the material, but we see reactivities around 200 joules per gram. And again, Leon also explained the test you need to do if you want to classify your material as an SCM. So you need to reach this 70%. What we are reaching at the moment is already above 90%. If we're replacing fly ash, if we're replacing slag, we see around 70% reactivity or strength activity index after 28 days. So very good results, which are clearly showing that this material can be used as an SCM. In terms of carbon footprint, we have received a third-party LCA, and meanwhile our product is also classified in the European database and also in the Dutch database. So the CO2 footprint of our activated cement paste is only 11 kilogram per ton. If you compare that with primary cement production, of course, depending on the efficiency of the cement plant, but the 750 is the European average today. So we have a 60 to 80 times less CO2 footprint than primary cement, which I think is very interesting with a local circular material. All of our process steps are patented. Basically, this is an old slide saying that we have two new patents published 2 months ago. So the ballistic separator you see here and the thermomechanical separator are industrial scale machines which have been operating here in the Netherlands for several years and have at the beginning of this year have been sent to the Ukraine and are operating now under the S3RU project in Kiev. I will show some pictures of that afterwards. But we have also meanwhile published a new patent for the ballistic separator. So we have made a lot of improvements to that machine to make it more intelligent, more reactive depending on what comes in, and adjustable on the spot. And we have also received a patent now for the entire process I just explained. So putting waste concrete into the machine, into the crushing, and getting activated cement paste out of it. And just a quick overview where we are as a company. So we have been operating these machines for many years. We have been doing a lot of tests on the equipment. Since 2018, we have processed, I think, more than 20,000 tons of waste concrete. We have used it also in different case studies. What you see here on the picture is dike protection structures, which we have produced and which are now controlled by the Dutch government. So they go there every 3 months to see also what is the long-term durability aspects of the material. We have been replacing in those structures up to 100% aggregates, up to 30% of cement, and also using our fine inert filler. So showing very good results, actually, strength developments, which were very close to primary cement. So these case studies are going on. We have also been building different structures like smaller bridges, pavements, foundations. All of that is being measured. But most important, and I will explain that in the next slides, is that we have launched a partnership here in the Netherlands with Dura Vermeer, which is the second biggest construction company in the country. And we are now building our first industrial scale plant, which will be able to process up to 500,000 tons of waste concrete per year. That plant will be operational from next year onwards. And we are just very close to signing a second plant agreement with a partner in Germany. So we're scaling up. We want to implement that technology globally now and make sure that this 3.5 billion tons of waste concrete is soon something which is being used and which is being used in a more upcycled way. So the plant we're building looks like this, and I don't want to go into all the details, but just that you see, this is what I explained on the flow sheet. We have the crushing down here, the ballistic separation, thermomechanical separation, all that. What you see here is the activation part, and then the storage for the powder material. This plant has a footprint of roughly 50 times 60 meters. And as I said, it will be operational next year, phase 1 in Q1 next year, and then 6 months later, the full plant will be operational. And we will start with processing 150,000 tons per year here due to the permits we have. So we will only operate 5 days per week, 8 hours per day. We have already signed offtake agreements, or at least LOIs, with 10 potential off-takers. So the market is very interested in receiving those goods and materials. And on the picture, you can see actually the location where it will be, so close to the water. We can receive concrete waste from the water side, but also can send our materials to the off-takers via that way, which of course is also a very efficient way of distributing the materials. So what are we planning as a company in the future? We are building this first of a kind plant now in order to demonstrate that whatever we have been evaluating in the lab, in the pilots in the last years, works also on fully industrial scale. This will be done next year. We want to build 7 more of this joint venture plants where we are part of the operation in strategic important locations worldwide. We need to prove that no matter what waste concrete feedstock we have, no matter what is the composition, that it works in our process. But we also want to demonstrate, of course, that the system economics works, that we can enter new markets with everything which is related to that, the marketing of the material, the certification of the material, finding new off-takers, all of that. And that's why we want to work in this joint venture structures with strong local partners who have already a presence in the market and who can help implementing that solution. After this first 2 phases, then we want to step back a little bit as the operating partner and go more into what we call a franchising phase, so that every recycling company, demolition company, concrete manufacturer, construction company in the world which believes this is a good concept can take our products, can take our portfolio, flange it to their existing portfolio, and we will then, of course, support with the technology, but also be a partner in bringing that products into the market and helping with servicing the plant moving onwards. Not to go too much into details, but it's important to understand that this is a concept which works without any subsidies, without any CO2 taxation, without any green premiums. It's a very solid business case. And of course, it depends on where you are in the world. These numbers are from the Netherlands. It is better or worse, but what we have seen, I think we have so far calculated around 60 to 80 business cases. It is super solid. So you can, in the Netherlands, with 1 ton of waste concrete, generate 40 euros of revenue, most of it coming, of course, from the activated cement paste and from the RCA. And the costs are relatively low. The bigger the plant, the better the economy of scale. But the EBITDA we have on this plant is very solid. It's a very solid business case. And yeah, now I'm coming. Just let me stop that for a second. Now that was the Everox part, and I already alluded to that. We started the S3ROU project last year, funded by Innovate UK, and with all the partners you see here. And I took the liberty to steal that wonderful video just to show who are the partners in the consortium. So I let it run in the background. The idea of this, of course, to evaluate also, as Leon alluded to, what to do better with end-of-life concrete, how to use it better than landfilling it or downcycling it. And yeah, the machines are now operating in Kiev, in the Ukraine. We have some industrial partners, we have some academic partners. Of course, ReThink is there also to support and to showcase our collaboration. And as I said, the machines which you saw in the picture in the Netherlands are now being built up in Kiev again. They have been commissioned a couple of months ago. One of our industrial partners, Ecoplus Logic, is operating them. And we're upscaling now. We're producing quite a lot of material, and the project will run until I think end of April next year, and then we will decide how to proceed. But it's, of course, it's a wonderful showcase also to see how does those machines work with the waste concrete which is available in the Ukraine, and how can we deal with other contaminations which are in the rubble which we find here. It's not only about plastics, wood, and glass. There's other contaminations, of course, which we find in the feedstock material, and we're learning a lot. And I think it's a wonderful collaboration. And if you look at the amounts, and maybe it's difficult to find reliable numbers, but what I know from the Ukrainian concrete sector, the demand for building is very high. It's actually double of the amount of the Netherlands, and of course there's an unfortunate reason for that. But roads and buildings have to be rebuilt. So we're looking at roughly a number above 20 million cubic meters of concrete, which needs to be produced every year. And the concrete waste only related to the war in the Ukraine is roughly 3 million tons. And out of that, we are only recycling 6%. So there's a massive opportunity to use more of that material in order to fill the gap and to have a more circular building industry, and also make sure that all this landfilling which happens at the moment is not required anymore. And I think that was my last slide. I hope I was not too fast, but I'm very happy to answer all of the questions which are coming, and I'm looking forward to that Q&A.
Thank you so much, Martin. I truly believe your unique process, your unique innovation is a way to give identity to waste. That was mentioned in the Leon's presentation, the words of Thomas Rau, that waste is something without an identity, material without identity. But you're kind of essential link to give this identity to a material and to really give value to it. And I really hope that after 2026, you will still consider Ukraine as one of the key location for your next plants. We will be very happy to work on that as well. Indeed, let's move on to the Q&A. We already got some questions, even in the registration form, and we are still receiving them right now. And I encourage everybody to ask your questions in the Q&A, but I will start from those that were asked before, and that is, let me see. Okay, so what is the cost, or let's say the price of recycled concrete in the European Union, and do you export it?
Okay, I guess the question goes more towards the finished product, not the feedstock material. What we are seeing here in the Netherlands, and of course it is very market dependent. We have to see how it goes in other European countries. But here in the Netherlands, since the market is already pretty well developed, there's a huge push by the government to use more recycled products. Actually, by 2026, it's forbidden to use recycled aggregates as road-based aggregates. So everything has to go down back into the construction, which is a very good initiative. So of course the prices are getting pretty high. But in theory, I would say in the European Union, as a rule of thumb, you can say that the aggregates can be sold at a comparable price to natural aggregates if the quality is the same, right? And that is very important. I mean, if you have water absorption levels which are for the coarse aggregates below 4 and for the fine aggregates below 7, you can replace a huge amount of natural aggregates in concrete, and then the prices can also be similar to natural aggregates. For the recycled or the activated cement paste, we're looking at an SCM. So we are roughly at 60 to 70% of the cement price in the country. And that really depends on how high the reactivity of the material is. In order to sell it at these prices, all materials have to be certified. This is very important. Without certification, of course, the prices will be much lower. Yeah?
So you have kind of certification that proves also your LCA result of 11 kilograms of CO2 in the activated cement paste, right?
Yeah. I mean, how you sell activated cement paste, there's different ways to do it. For example, you can sell it to cement manufacturers. All over Europe, we have the DIN EN 197-6, which allows the use of recycled cement fines up to 35%, depending on the application. So this is possible all over Europe if you blend it into cement. Our business model is more focusing on replacing cement directly in concrete, and that is a very local business, right? Because the
Yeah.
concrete regulations are very, very local. So we need to see where we are. Here in the Netherlands, we're at the moment working together with the government on amending the local concrete legislation. So by middle of next year, we have formed a working group of 20 people, different participants from the industry, from academia, from the legislation side. And we're doing now a very intense testing program. And then this working group will write a recommendation. And with that recommendation, we will change the legislation, and we will have a concrete norm which allows to replace cement with our material as a reactive binder. And I'm very happy when this document is done, because then we can take it to different places in all over the world and say, look here, all these experts have already done this great job, and then hopefully it's easier the next time to get something like this also into other concretes. But it is not easy. Yeah.
Thank you so much. So there are some questions already which were asked which were answered during the presentation itself, like about LCA and about costs, etc. So very funny, but there you go, business opportunity. Does S3 provide concrete from reused part in Ukraine? What regions in Ukraine can I order this concrete?
Sorry for me answering again, but I think where we are right now is that we're already producing, and I have to say that the plant which is operating in the Ukraine at the moment is not the entire plant I showed in my presentation, right? So it has the two middle process steps, and it has a different crushing at the beginning, but we're not yet activating the fines coming out of that. So what we can produce in that plant in the Ukraine is recycled coarse aggregates, recycled fine aggregates, and some kind of cement or concrete fines, but it will be very difficult to use them already in a commercial way. And we're also at the moment still commissioning and upscaling the plant. So at the moment, it is an academic project, and we're using the materials in order to understand better how it works. But as you also said, we are working very intensively with especially with the local Ukrainian partners to have a commercial solution ready when this project runs out. So I think hopefully soon it will be ready, available as a commercial product. Yeah.
Yes, thank you so much. Now, the next one. How do you mitigate safety risks like asbestos exposure? And if none of you wants to answer, I could. So the asbestos situation is difficult in Ukraine because we have a lot of it, and well, we basically don't have any mitigation strategies developed by the government in place. So many international organizations and donors, when entering this sector of debris management, they started developing their own operating procedures, their own guidelines, how to manage asbestos at sites, including JICA, including UNDP and others. There is an enormous working group created by UNEP on asbestos, and yeah, it's still going on. The problem is that all those guidelines and standard operating procedures, they do not cover the upcycling process. So what they describe is how you have to behave when you transport potentially asbestos-containing materials from destruction site to landfill. So it's all about landfilling. But when it comes to taking materials from destruction site or landfill and then trying to upcycle it, there is no operating procedure developed whatsoever, and that's something what we are developing right now. Meanwhile, what is being researched within the S3 project, the material that is coming in, is asbestos free because we take it from other crushers that were located in Borodyanka and that were provided by JICA, and those guys have all the equipment to test for asbestos. So when it's coming out, we know it's asbestos free. So in this particular R&D phase, we don't have that problem, but it is essential that we develop operating procedures for asbestos handling for all processes, for upcycling as well, and that we keep people and environment safe. One of the approaches is, of course, remotely operated equipment, and yeah, we all have seen that test lately by the Japanese over here. But yeah, we will see. We will see how it goes. So for now, S3 material coming into the Everox equipment is asbestos free, and for the future, we are developing this SOPs right now. Next question is okay, to what extent, I'm just translating from Ukrainian, to what extent off-takers or construction companies are ready to use second-hand, like recycled concrete? To what extent? I think people are asking about Ukrainian ones, so I don't know if you guys want to reply or shall I do that?
Yeah, I think it's the construction industry, with all respect, as we know it, is very, very conservative. So, which is good because we're talking about serious risks when using new materials. So it has to be solid. The good thing about recycled concrete is that all the elements of it was already a natural building material, primary product. So it's basically about how to clean them, how to activate them again, and then you can use the same standards as you used before. And that is also what we see, at least with a lot of construction companies. It's much easier to discuss such type of secondary products than if you go for steel slags or something, I don't know, which is coming from which is a totally new application. So first of all, positive. Second part of the question is the certification, which I already answered. If there is a certification available, then the willingness to use them is very high, because then, of course, you play with the rules. And the third aspect is the push of the government, of course. There has to be a push to use this product, otherwise nobody will use it. If there's not an economic push or a legislative push, then yeah, people will stay to do what they did the last 100 years. This is
Yeah, that's true in all areas of life. But in Ukraine, we obviously don't have neither economic push nor legislative push yet, but both are coming, I hope. What challenges did you encounter when standardizing the material? I don't know question to whom that is, because both speakers spoke about materials and research, but maybe you both can reply.
I mean, I would probably defer to Martin, because we're academics who haven't tried to standardize anything. We've used various standards for testing, but not for actually validating performance. So I think it's more for Martin.
Yeah, it is a very valid question, of course, specifically when you have different feedstock materials. And also what we've been doing the last years is, of course, testing the process parameters to evaluate what is the best process parameters in our entire setup to reach the highest possible reactivity. And when I talk about process parameters, there's so many variables. It's about pressure and decarbonation. It's about humidity. It's about temperature. It's about CO2 flow and concentration. So all of that has been tested quite a lot. We know, meanwhile, what is the best setup, and only since 3 months we are capable of producing the same quality of output material with different feedstocks. So it took us a very long time to standardize this, but now we're able to do it, and we haven't yet scaled that up to the big plant we're building now, right? So this is in our big size pilot where we are carbonating now, but it is a challenge. And what we're building right now is a artificial intelligence or an automation concept on the plant, which will do that for us in the future. Because also in the future, when the full plants are up and running, we'll have huge variations in input material. Some feedstock will come from a bridge, some will come from a pavement or an easy slab. So the quality of that material will be totally different. And that's why we will have a lot of sensors in the plant. We have, I think, up to 15 high-speed cameras, which in front of every process step determine the quality, the composition of the material, and then adjust the process conditions in the downstream process accordingly. So you can either crush harder or less hard depending on what goes in, or you can change the speed of the ballistic separator, or you can change the pressure of the air knife. All of that is automatic, so that we just have a system which can do the work for us and can make sure that what comes out of the end has a constant quality. Maybe, of course, the yield will change. So the less good the feedstock material is, the less cement we will get out of it. But the quality has to stay constant. Otherwise, we cannot use it and we cannot sell it.
Okay. And the next one, Leon, could you please assess what is more economically viable, carbonation or heating aggregates?
Oh, I feel like I just keep batting these questions away here. We haven't actually looked at the economic viability of this. We've been looking at the technical performance to begin with. The next stages are to look at both the carbon input associated with this processing, and if we could do some financial modeling, it would be interesting. I will say there are a whole host of non-technical barriers to what we've been doing, including, one of the things is scale up and doing things, processing in real time, which is something that Everox are addressing. They're overcoming those problems. We just used a carbonation chamber in a laboratory to carbonate these materials. So I don't know is the honest answer. But the next step would be to actually look at the carbon intensity of this and try and see some modeling as to what would be most viable.
Martin, do you know?
My answer is the same. I don't know, because we were from the beginning focusing on the sustainability aspects. We never thought about using a lot of energy in order to. I mean, the more energy you use, the more reactive you can make the product. The more money you can get for it on the market. This is obvious, but we still believe that we want to create a product which is good enough to be used as a building material, but with the lowest possible energy footprint, right? And also saying that carbon footprint, and that is always our intention. We never tried using heat.
Cool. Well, yeah. Next one, we have to speed up because we have just 6 minutes left, I guess. What kind of economic incentive could improve the use of recycled concrete in Ukraine. What is the experience in your country? Well, yeah, to make it, how can we push economically this process? Well, obviously with the regulation, but what kind of regulation?
Yeah. I mean, what is important that you found some kind of coalition of people who really want to use this material, and that needs to have different aspects. You need to have off-takers who are on board, the construction companies, the government needs to be on board. So the first step is really providing legislation, because nobody will use a building material which is not certified. The risk is far too big, right? So you really need to have this certification, this legislation available. And if that is the case, and this can be done relatively fast, if the authorities who are responsible for putting the norms and regulations for construction are willing to do something like this, we can work with them together and get it in place. And then when this is in place, the off-takers will be interested. Specifically, they are using already fly ash, they're using slag, they're using things which they have to import maybe. If there's another alternative, then it's only a question of price, but they will use it. So putting the legislation in place is maybe the most important step forward.
Yes, I agree with you, Martin. Let's just clarify, who has to certify the material? Could those be local Ukrainian certification bodies, conventional conservative ones, or do you mean any international certification?
No, it can be local, definitely. I mean, we're also using local ones here in the Netherlands, SGS or Como or Kiva, whatever they are called. Of course, some of them are also international, but it doesn't matter. It's about the legislation. Once the legislation is right, then the legislation body can decide how to certify, and then actually we, as a producer of the material, need to certify it in line with the legislation using local certification bodies. Yeah.
Thank you so much. A little bit overlap in next question, but I just, with the equal respect to all questions, I will read it. Martin, could you tell us what next milestones are for you to make your concrete to become widely available technology, legislation-wise?
Yeah, and I think I explained it during the presentation. So if you look at the legislation side, using recycled or activated cement paste in cement is possible in many parts of the world. I think even in the Ukraine, if you stick to the European norms, the EN 197-6 allows already to blend up to 35% of that material into cement and make a new cement type out of that, which then can be used in concrete. So that is the I would say number one, which works in all over Europe, which works in the US, which works in the UK already according to British standards. I'm not sure about the Asian Pacific region, but I think that works pretty good. If we want to use it directly in concrete, it's so complex because it really depends on the regional legislation. Even inside the Ukraine, there might be different concrete norms depending on where you are in the country. And so I think there we go back to and I hope Europe will take that step moving forward to have more performance-based standards available, which I think is happening, but it's not there yet. And if you have performance-based standard, then of course it's not about how many percentage you put into the product. It's about how does the product perform, and then it's much easier to use more and use it more widely.
Yeah, absolutely. Absolutely. Thank you for this. Finally, we have one question left, and it's a very simple one, but I need to make a small adjustment to it. So it says, thanks for all your presentations. How much 1 ton of new material concrete and 1 ton of recycled concrete costs? What is the price difference? But let's make an assumption. So I'm adding from my side. let's make an assumption that you are adding those 35% that are allowed. So what will be the price difference of 1 ton of concrete, ready concrete?
So if you use the same water, you use the same aggregates, and I said that the aggregates are at the same price like the primary products, the cost savings you make on the cement side. So you save 70% of the cost on 30% of the material, which gives you roughly 20% savings.
So it's cheaper. Recycled concrete will be cheaper than virgin one?
It will be
Oh,
cheaper.
like
Yes.
the new
It
one?
will be
Yeah,
cheaper.
in the Netherlands.
Yeah, it should be everywhere, because I think that that concept that you can bring the aggregates into the market at the same price like the primary products is the same, right? So you're only saving on the cement part, but there you're saving quite a lot. Yeah, but I made a mistake. So you're saving 30% of the price on 30% of the material. So saving will be roughly 10% if you want to. Yeah.
Okay. Okay, but that's still really, really valid and significant. All right, guys, we are just perfectly. Thank you very much. Very interesting and valuable. Yes, thank you very much, Julio Mozhova. We are perfectly ending at 12:30 Kyiv time. Thank you, Leon. Thank you, Martin, for joining, for your super interesting, insightful speeches and presentations. We really hope that we will carry on with the S3 and next projects to make Ukraine's reconstruction as circular and sustainable as possible. And I really, really hope that you guys will have your important role in this process. I wish everybody a pleasant and fruitful day. See you next time.
Thank you so much. All the best and
Thank,
stay safe. Bye.
thank
Thank
you.
you. Bye bye.
Bye.